Hello and welcome to Chapter 6, Section 2, Properties of Rational Exponents. You've probably seen properties of rational exponents before, but maybe not all of these that you see here. So we're going to go ahead and use them in examples so that you know how to apply them to problems. Now in example 1, it says use the properties of rational exponents to simplify each expression. And what that means is we're going to use those properties in the table above, and I'm just going to summarize them as we go. Now for part A, we have a number times a number, and they each have exponents. When you have the same number when you have the same number and they're raised to different exponents, you add the exponents. So this is really just 13 to the 1/3 plus 1/6 power. Okay, when you add 1/3 and 1/6, you end up with 3/6, which is the same as 1/2. And that's it, that's all you're doing. Now, if you have something outside of your parentheses, you have to first distribute it in, and then realize that you have a power raised to a power. When you have a power raised to a power, you multiply them. So when you have two things multiplied together, you add, but when you have the power to a power, you multiply. Now 5 times 1/5 is just 5, and 5 times 1/4 is 8 to the 5/4 power. And that's it. That's all you're doing. On part B, we're going to distribute that again. Okay, and this time, negative 1/3 times 3 is always going to end up being negative 1. They each have that as the exponent. So we end up with 12 to the negative 1 times 9 to the negative 1. Well, if you look at that table above, you might notice that if you have a negative exponent, your entire thing goes to the denominator of a fraction, as long as what you're multiplying isn't 0. So we're going to take these, and this is going to be the same as 1 over 12 times 9. Notice when you put it in the denominator, your exponent is suddenly, instantly positive. Then all you have to do is multiply the numbers, and 12 times 9 is 108. And so that's your answer, 1 over 108. Let's do another one. Well, on E, we really have something divided by something. Right? And when you have something divided by something, when you have a quotient of powers, you're taking your exponents and subtracting them. And really, secretly, this 8 has a 1 as an exponent. So this is the same thing as 8 to the 1 minus 1/9. All right, because you're subtracting your exponents because it's division. Well, 1 minus 1/9 is 8/9. So it's 8 to the 8 over 9. And that's it. Now we also have a property in part C. If you look down here, we're going to end up distributing that 3. But before we do anything, because 56 is raised to the 1/4 and 8 is raised to the 1/4, I can change that because they have the same exponent. And I can just divide 56 by 8. Well, 56 divided by 8 is 7 to the 1/4 because they already had the 1/4. And then the 3 is on the outside still. And then because we have a power to a power, we're going to multiply them. So we have 7 to the 3 over 4. All right, so make sure you're using your table. Now, on this next page, we're going to use properties of radicals, and we know properties of radicals. We've actually used some of them, but we haven't used them for the 3rd root and the 4th root and 5th root and so on. We've only used it for a square root, but we're going to do a very similar concept here. Now, on part A in example 2, we have to take this 4 and start dividing. So 4 is divisible by 2, and we get 2. All right, great. 128, however, is a little more involved. So 128 is divisible by 2, we get 64, which is divisible by 2, we get 32, which is divisible by 2 to get 16, which is divisible by 2 to get 8, which is divisible by 2 to get 4, which is divisible by 2 to get 2. All right, so when we did this before, we were looking for pairs because it was a square root. Now we have a cube root. So this time we're actually looking for multiples of 3. Right, so to simplify things, I'm going to take these and put them underneath my root. And because they're multiplied, we can actually put everything under the root at the same time. So because of the 4, we had 2 of them. When we're talking about the 128, we have 1, 2, 3, 4, 5, 6, 7 of them. So I'm going to put 1, 2, 3, 4, 5, 6, 7 of them. And now I'm going to circle multiples of 3 because it's the cube root. So I have this 3, and this 3. And just like when we did with square roots, we're going to take this and pull it out, and just have 1 to represent that group of 3 for each of them. There ends up being nothing left under the radical, and I really just have 2 times 2 times 2. Well, 2 times 2 times 2 is 8, and that's the answer. Let's come over here to the example B. Now we have 192 over 6, and they're both under the 5th root. So just like when we had the same exponents, we have the same root. That means we can divide. So we really have the 5th root of 192 over 6. You're allowed to do that. Luckily for us, 192 is divisible by 6. It's 32. So now we need to see, okay, what's 32 divisible by? Well, let's divide it. 32 is divisible by 2 to get 16, which is divisible by 2 to get 8, which is divisible by 2 to get 4, which is divisible by 2 to get 2. Well, that means we have 1, 2, 3, 4, 5 things on the outside. Well, we have a 5th root. So if we have 5 things on the inside, because we have 2 times 2 times 2 times 2 times 2, we have to circle all of them in order to be able to take something out, and we can, because there are 5 of them, and the answer is 2. So let's go on to example 3. In example 3, we're writing each expression in simplest form, and we're essentially doing what we just did. Because it's 500, we need to figure out what goes into 500. Well, I'm going to start by writing it down here so I have space. We'll have 500 is divisible by 2 to get 250, which is divisible by 2 to get 125. Well, that's not divisible by 2 or 3 or 5. Yeah, it's divisible by 5. We get 25, which is divisible by 5 to get 5. So I'm going to rewrite this as the cube root of 2 times 2 times 5 times 5 times 5. And remember, I can take out groups of 3 because it is a cube root, so I can only take out this grouping of 5. And when I take out that grouping of 5, we're going to have 5 on the outside to represent that group. Then I'm going to take 2 times 2 and just multiply them together because they didn't have a group of 3, and I get 4, and that's our answer. Now remember when we started rationalizing denominators? We had to rewrite things so that the denominator ended up not having a root in it because it's against the rules to have a root in your denominator. So I'm just going to rewrite this, and I'm going to remember that 2 times 2 is 4. So 19 is prime. That means we can't do anything with that. But we really have the 4th root of 2 times 2. Now remember, our goal is to get a number in the denominator, so I'm going to need a group of 4 this time instead of a group of 2 or a group of 3. We need a group of 4. Right now I have 2 of them. Well, to get a group of 4, I'm going to need 2 more. So I'm going to multiply by 2 times 2 underneath my 4th root. That's going to give me my group of 4 that I need to be able to pull it out. But then you have to remember that what you do at the bottom, you have to do the top. So we really have the 4th root of 2 times 2, which was 4. Well, because I could take that group out, I have 2 left on the bottom, and on top I have whatever 4 times 19 is, which is 76. So let's move on down. In example 4, we're going to simplify each expression. When you're talking about addition and subtraction, you just have to make sure you have like terms. And I'm saying that with quotes around it because like terms are normally letters. Here, they're roots. So if I have 6 roots of 17, if I have 1 6th root of 17 plus 9 6th root of 17s, we secretly have 10 6 roots of 17. All right, because this was just a 1, and we're adding them together. The same thing happens in part B. They're both 7 to the 1/3 power. I have 5 of them, and I'm adding 6 of them. Well, 5 plus 6 is just 11 times 7 to the 1/3 power. And we're not going to distribute that or anything. We're just going to leave it like that. Now, what happens if you get something like C, where 48 is not the same as the 4th root of 3? Well, then you have to start thinking, maybe 48 has something we can take out of it. So we come over here to the side. We write 48 and we see what it's divisible by. Well, it's divisible by 2 to get 24, which is divisible by 2 to get 12, which is divisible by 2 to get 6, which is divisible by 2 to get 3. So we do have that group of 4 in there. So we can take out all of those 2's with one representative. So we really have 2 4th root of 3 minus 1 4th root of 3. Well, 2 minus 1 is just 1 4th root. of 3. And of course, that 1 is not necessary to write. I just wrote it so you could see it and notice where I'm coming from. Now, we're going to keep doing this idea, right? We're going to keep applying this. It's going to continue throughout the rest of the notes. And it's actually pretty simple, but what you do have to remember is that if you have an odd root, you're allowed to get a negative answer. When you have a even root, so an even root like the square root, right, which we've talked about, or a fourth root, or a sixth root, you cannot get a negative answer. And at that point, you have to start putting absolute values around your answers. So let me show you what this looks like. In part A, we have an odd root, so we actually don't have to worry about it at all. But we have letters now. And so it's this really cool thing where this inside exponent can just be divided by that. And if it divides evenly, then that's how many you're going to have. So for instance, 12 divided by 3 is 4. That means my answer ends up being d to the 4th power. Now I still have to worry about that 27. Luckily for us, 27 is a perfect cube. The cube root of 27 is 3, and I'm done. So let's go ahead and do part B. Now we have an even root, so we might have to worry about our absolute value. Well, let's see. We're going to take 6 and divide by 6. Well, what's 6 divided by 6? 1. It does go in evenly, which means we'll just end up with 1x on the outside. Over, well, now we have 12. Now we have 12 divided by 6. Well, 12 divided by 6 is 2, so you end up with y squared. Now you do have to remember that when you square something, no matter what it is, it's always going to end up being positive. So when I'm dealing with my absolute value, I don't have to worry about it if it's squared. If it's an odd power, though, I've now got to stick these absolute values around it just to make sure that whatever I'm plugging in is still positive. Let's go to the next page. Write each expression in simplest form, assume all variables are positive. By assuming all variables are positive, I don't have to worry about those the absolute value bars anymore. If it doesn't say that, though, then you have to put your absolute value bars. And we're going to start dividing. So, let's see. I'm going to put my fourth root just to set it up in case I have anything left over. And I'm going to come over here and start dividing 48. Well, 48 is divisible by 2 to get 24, which is divisible by 2 to get 12, which is divisible by 2 to get 6, which is divisible by 2 to get 3. And because I'm dealing with the fourth root, I can only take out multiples of 4, so we're here, right? Which means 3 is going to be on the left. 3 is going to be left inside, and my 2 is going to be out front. Now I do need to make sure I leave space just in case anything happens, so let me a little more space. All right. Now let's take our 11 and divide it by 4. Well, 11 divides by 4 2 times, so we'll end up with a squared, but then you have to worry about what's left over. So if I multiply 4 by 2, I get 8, 9, 10, 11. It takes me 3 more spots to get to 4. So I'm left with 3 A's on the inside. All right, let's do that again. B, which is 4 divided by 4, well, that divides evenly. And we're assuming that all variables are positive, so I can just put a B outside. I don't have to worry about anything left over on the inside. Now we have 13 divided by 4. 13 divides by 4 3 times, so we have C to the 3rd power, but it doesn't divide evenly 3 times. 3 times 4 is 12. We're left with 1 to get to 13, so we have C on the outside. And this is our final answer. Let's do that again. Well, first, on part B, we have to simplify our radical that's in the denominator, okay? Because we have a root in the denominator, we're actually going to have to rationalize our denominator here. My x squared is not going to change. That's still x squared on top. But 13 divided by 3, well, it divides 4 times. So we have y to the 4th outside, and then we have our cube root of y because we end up with 1 left over. Now our job is to make sure that there are no roots in our denominator. I have 1, I need 3. Well, to get 3, I'm going to need 2 more. Right, so that's going to be y squared. What you do on the bottom, you have to do on the top. Well, that means I can take this out. So I actually end up with x squared then my third root of y squared over y to the fourth times y, which is y to the fifth power. And we're done with that problem. Now on part C, remember when you have exponents in the when you have something in the top and the bottom, your exponents are subtracted. So we have 16 divided by 8. Well, we all know that that's 2. We have x to the first power minus 2/3, which is just x to the 1/3. We have y to the 1/3 and nothing on the bottom, so we could just leave that as y to the 1/3. And then z to the negative 4. If I want to take that and make that positive, which I do, I always want to make it as positive as possible. I'm going to take that negative 4 and I'm going to stick it on top, so it's no longer in the denominator, and because I moved it, you can move it and make the exponent positive. And so there's our answer. Last problem. Perform the operation. On example 7, part A, we have 6 cube roots of x plus 2 cube roots of x. Well, that's just 8 cube roots of x, and we call it a day. On part B, though, it's a little more complicated. First, let's look at the 3p to the 6th power. Well, 6 is bigger than 4. That means I'm going to be able to take something out. 6 divided by 4 is 1, so we end up with 16p on the outside, fourth root of 3p, and what's left over? Well, if I have 6 divided by 4, I get 1 with a remainder of 2, so it's 3p squared. For the 48, we've actually done this a couple of times now. It ends up being 2, and then underneath our root we have 3. All right, we already had a p outside, and then p squared is smaller than p to the 4th power, so we don't have to deal with that either. And now our insides match. They had to match before we could do anything with this. 6p minus 2p is just 14p, and then our fourth root of 3p squared. That's it. Sorry it was so long. Have a great day.